Hi everyone, my name is Fetiye YAKIN. I am the PhD candidate in Sabanci University and my department is the manufacturing engineering. Today I'm going to talk about an experimental investigation of static and dynamic mechanical properties of different ply orientation of carbon fiber reinforced composite under elevated service temperatures. And this is my outline. Firstly, I want to give information what is the composite, and also I want to give the content of my current studies. And what is the composite? Composites are a combination of material different in composition where the individual constituents retain their separate identities. In the below part of this explanation, you can see the fiber impregnated with matrix, and also depends on the fiber type, depends on the matrix type. The composite materials are used many engineering applications where the aerospace, shipbuilding, defense, biomedical, building, railways, automotive, and etc. In my study, as you can see in the figure, the Boeing part and the Boeing part, what materials are used in the Boeing parts, body parts, and the composites are have the highest percentage of composite material, has the high percentage of usage for the Boeing body and also aerospace, defense, and aircraft applications. Because carbon fiber reinforcements composite material have several advantages such as lightweight, high strength, stiffness profile, load resistance, high toughness, and the Taylor mechanical and the thermal properties. These engineering applications are preferred to use the composite material. In my studies, I used to investigate the relations between the fiber orientation, fiber architecture with respect to the temperature change, and with respect to the different process parameters, and the not process parameter, the manufacturing parameter, sorry for that. And I used the two different type of the fiber orientation, the unidirectional 0 degree and the cross ply, the 0 and the 90 degree carbon fiber reinforced polymer composites are used. And as I mentioned before, the fibers orientations and the layup versus have a crucial role in the desirable mechanical performance and microstructure of the composite materials. And also the elevated temperature environment mainly affect the mechanical performance and the failure types of the carbon fiber reinforcement polymers due to the polymer matrix degradation and the weakening interfacial adhesion between fiber and matrix. And also, moreover, the manufacturing process enables the variation on the mechanical properties of the composite manufacturing. In traditional defense and the aerospace application, autoclave curing is mainly used for the less void content and high fiber volume formation. And because the autoclave curing has applied the high pressure and high temperature, therefore the less void content and the high fiber volume fraction are getting from the autoclave curing. However, vacuum bag only is a great candidate for the autoclave curing, because autoclave curing has a lot of drawbacks such as time consuming, energy consuming, and the final part size limitation. Vacuum bag only is a great candidate for the getting the final part of the composite manufacturing. However, it should be investigating for the adding some kind of parameters. For my study, the major point of my study is the effect of the ply angle lamination and vacuum bag on the process for the thermoset matrix composite, and also depends on the effect of ply angle as a function of temperature. The failure type and the mechanical behavior of composites are changed. Also, the fiber volume fraction and the manufacturing process are similar for our both lamination. Therefore, all upon these information, the aim of our study is to investigate the effect of the static and dynamic mechanical behavior and the failure type variation on two different ply angle, cross ply and unidirectional thermoset-based composite lamination at the elevated temperature. In the left part, you can see our prepreg. The prepreg name is the Axiom, which is bought by the Corsa. And you can see the fiber type and the weight area of the fabric and the epoxy resin type, the epoxy resin percentage, and the glass transition temperature of the composites. And the right part of you can see the manufacturing step of our composite lamination. We use hand layup, and also we use the peel ply and the breather fabric. We apply the 1 atm pressure, and these laminates were waited to 24 hours before the oven curing step. And the last part, you can see the cured lamination. And after we got the composite laminates, we applied both characterization experiments and the mechanical test. In the left part, you can see that our experimental procedures divided the 4 parts: differential scanning colorimetry, fiber volume fraction, and void content. In the one part is for the characterization experimental part. The second part is the dynamic mechanical analysis with temperature range. And the third part is the static mechanical analysis, interlaminar shear strength, and for the room temperature 110 to 170 degrees. And the last part of the optic microscope and the detection of the failure type. This optic microscope also the proven of the interlaminar shear strength values, because the test specimen was exposed to the interlaminar shear strength, and after that we got the image from these test specimen. In the figure 2, you can see the short beam shear test setup with the specimen. For the result and discussion, in the figure 3, you can see the differential scanning colorimetry curves for the unidirectional and the cross ply. And as I said that in the table 1, you can see the TG value, fiber volume fraction, and the void percentage value for the UD and cross ply. You can see the different, two different glass transition temperature from the DMA and the differential scanning colorimetry. We couldn't use the glass transition temperature value from the DCG because composite materials are the viscoelastic materials. Therefore, the differential scanning colorimetry only give the clue about our plates are completely curing or not in my studies. And also, I want to tell that you can see that the fiber orientation could not affect the glass transition temperature and the fiber volume fraction value. However, and the fiber orientation affect the void percentage content with the vacuum bag only process. And the second part of the result and discussion, I want to show the short beam strength test and the dynamic mechanical analysis test, and compare with each other with the static and dynamic mechanical results. In the first part, figure 4, you can see the ILSS result. In the left part, ACE belongs to the unidirectional, and the BDF part belongs to for the figure 4 belongs to the cross ply. And for the failure type, you can see the unidirectional shows the shear failure at the higher temperature, whereas the cross ply shows the brittle failure in the higher temperatures. When we look at the delamination activation energies, the UD delamination energy decreases gradually. However, the cross-ply activation delamination energy decrease dramatically. When we look at the dynamic mechanical analysis results, we can see that the unidirectional storage modulus value is higher than the cross-ply. However, at the 110 and 170 degrees, the cross-ply storage modulus are higher than the unidirectional. This is not acceptable behavior, by the way. And also in these dynamic mechanical analysis results, we might say the molecular weight or the damping factor or the cross-link density. However, our study are only focused on the how the elevated temperature or how the temperature affect the fiber orientation with vacuum back only process. And the third part is relates with the optic microscopy. Firstly, these test specimens are exposed to the short beam test, ILSS, and with the three different test temperature environment. And after that, we got this image from the optical microscope. Figure 6, you can see the microscope image of the UV composites. Figure 7, microscope image of the cross-ply composites. The crack first I want to talk about the unidirectional. The crack formation was observed at the free edge in the room temperature for the UV, while when the temperature is increased, the crack formation was occurred in the middle region, and this is the result of the local stress variation. And this local stress variation leads to the residual stress variation in the unidirectional, and this residual stress variation reduce the stiffness and the brittleness of the unidirectional specimens. And also in the 110 degrees in the around the TG or slightly above the TG, you can see the fiber pull out. This can be the reason of the polymer matrix degradation. In the highest degree, 170 degree, you can see the minor delamination due to the because our matrix completely degrade, and therefore this degradation leads to the ductility of our matrix specimen. And as you can see, we can conclude that the cohesive damage occurs in unidirectional for the interlaminar region with respect this kind of the failure type. And on the other hand, when we look at the cross-ply lamination, as I said before, the void content is less than the unidirectional. However, you can see the intimate contact is degrees or less than the unidirectional as well, due to the fiber orientation of the composite lamination. And also these degrees intimate content leads to decrease the interfacial bonding. And for the cross-ply lamination, you can see the different kinds of the failure type, the fiber breakage, interface failure, intraply cracking, and especially in the around the TG and above the TG, 110 and 170 degrees. Also, we could observe that the bending effect is predominant in the cross-ply laminations, and also in cross-ply laminations, void acts as a stress concentration under the static loading. Therefore, we can say that even if our void content is less than the unidirectional, we can getting the different kind of failure type for the cross-ply. Also, composite divided into two phase, fiber phase and the matrix phase. The fiber phase carry the load, the matrix phase dissipate the load. Because in the cross-ply nature, the 90 degree of the lamination cannot hold the load, cannot carry the load very well. Therefore, it can also, the optic microscope is the proof that why our ILSS results were got like that. In a conclusion and the future aspect, the primary conclusion drawn from the experiment and analysis result that fiber volume fraction and glass transition temperature did not yield the different values of the each fiber orientation. However, the short beam strength test elucidate that the unidirectional composite demonstrate the higher interlaminar shear strength value than cross-ply for all studies test temperature respectively. Also, the activation energy was decreased gradually for the unidirectional composite as a function of temperature, while the activation energy, or like the elimination energy, of the cross-ply composite demonstrate dramatically drop around and above the TG values. Besides, optical microscope examines not only the explain of the drops of the ILSS values and also elucidates that the variation of the damage mechanism depending upon the fiber orientation as a function of temperature. The fiber breakage and pull-out failure were observed in the UD composite. However, the intraply cracks were detected due to the void formation, poor matrix, fiber alignments for the cross-ply fiber orientation. In future aspect, from getting all of the conclusion for all the results, the unidirectional and cross-ply lamination will be produced by the automatic fiber placement robotic machine, and we expose the vacuum bag only process by variation on the process parameter. Also, the cure cycle is really important topic for the increasing the fiber volume fraction and decreasing the void content. The cure cycle optimization will be applied to the our prep which bought from the Corsa for both fiber orientation lamination, decreasing void content, and increasing the glass transition temperature value. Thank you for your attention. Any question, I can answer it. Thank you.